All right, so we started off with the function square root of x minus 2, and we drew the graph. We came up with the derivative. F prime of x was 1 over 2 square root of x minus 2. We said that this function was continuous for all x greater than or equal to 2. That means that the function value exists at 2 and everywhere going to the right. Remember, for the left endpoint, we don't have to do the three-step definition of continuity. Because it's the left endpoint of the graph, we only need to see that the limit from the right is equal to the function value. So it's continuous for all values greater than or equal to 2. What we were then about to talk about was whether or not the function was differentiable. So just to review, a function is differentiable, we say, if its derivative exists at that point. All right? So if we come to this graph, if we start drawing tangent lines on the right-hand side and start coming back to the left, let's see what the graph would look like. There's a tangent line. Here's a tangent line. There's a tangent line. There's a tangent line. What does the tangent line look like at 2? I drew it in green yesterday. Not horizontal, it's a vertical. So let's go ahead and say this. At x equals 2, we have a vertical tangent line. So the function exists there, which is why we're able to have a tangent line at all. But what is the slope of a vertical line? Infinity. And since infinity is not a number, we say the derivative does not exist there. The derivative does not exist then at 2, even though the function value does. Now, one last thing before we make the concluding statement. Would the derivative exist over here at x equals negative 1, let's say? Does it even make sense to talk about the derivative to the left of 2? No, because there's no graph. There's no point, so what's the point, right? So we could say then that this function is differentiable for all x strictly greater than 2. And that's kind of interesting. The function's continuous at 2, but it's not differentiable at 2. So there are values that are in the domain of a function where the derivative fails to exist, and this is the first example you have of one. So anytime you have a vertical tangent line on a graph, you're going to have a slope of infinity or negative infinity. The derivative will not exist, even though the function value might. Okay, so the last thing we're going to do here is write the equation of the tangent line at x equals 27. So if we come back up to the graph, I drew that yesterday. Here's 27 right there. If we extend the graph out like that, 27 might be right there. And so the tangent line would look something like this. You can snap it too. There you go. So it's going to be a pretty flat line. What do we need for the equation of a tangent line? Yeah, we're going to need this. That gives us the slope, right? We could get by with 2 points, but we don't have 2 points. We only have the 1 point. So we're going to need the point of tangency, and we're going to need the slope. So let's go ahead and find the point first. At x equals 27, the point's going to be 27 f of 27, right? We're going back to our y value machine. So let's go back to the top and see what that's equal to. If I find my f of x function, it's the original one way up here. What do I get when I plug in a 27? I get the square root of 25, which of course is 5. Yeah, so that's the y value. 27 is the x, 5 is the y value. And now the slope is going to be f prime of 27, slope at a point. And we did find that yesterday on part B to be 1/10. The slope is 1/10, which is reasonable for that slope because it's going up 1 vertically for every 10 it's moving to the right, which means it's pretty flat. Now that you have the point and the slope, we're going to take the point-slope formula and modify it. Here's what the point-slope formula looks like from Algebra 1. It's y minus y sub 1 equals m times x minus x sub 1. And all that is that's a derivation from the difference quotient. If you take y minus y sub 1 over x minus x sub 1 equals m, just multiply both sides by the denominator. What Taylor form does is it simply takes the point-slope form and it solves it for y by adding y sub 1 to both sides. So the Taylor form is y equals y sub 1 plus m times x minus x sub 1. And all year long, for every equation that we are going to construct, we're going to use the Taylor form pretty much exclusively, unless we happen to be handed the slope and the y-intercept, in which case slope-intercept form is pretty nice. But Taylor form, okay? Y equals the y value that you're given plus the slope times x minus the x value. So we have all the information. We're ready to go. The equation of our tangent line, well, let me go ahead and write the equation of tangent line. It's going to be y equals the y value, which we found to be 5, plus the slope, which is 1/10 times x minus the x value of 27. So we'll be writing equations of tangent lines on and off all year long. We did the 1/10 yesterday. I wanted to find the slope at 27, so I plugged it into here. F prime of 27, because remember this is your slope machine. It's 1/2 times the square root of 25, which is... So if we hadn't done that yesterday, we would have, we would do that. Yeah, you're going to need to derive F prime. Okay, now I'm going to add one other question here. There is another line that's significant, and I'll use red for it. It comes in right here at the same point, and it's perpendicular to the tangent line. Does anyone know what the name of a line is that's perpendicular to a given line? That is a great guess. No one's ever said cotangent. But if this is the tangent line, cotangent would be a great name for it. I like that. If we were at the math voting place, wherever they decide on the name, I would vote for that if you threw it out there. Actually, it's not the cotangent line. Think back to physics when you have these little schematics. When you have like a block on an inclined plane, there's the center of its gravity. Here's little g working. There's the force being pulled on it. Here's the force of friction. You had another force that came up perpendicular to the plane, which was called the what force? The normal force. Okay, the normal force was always perpendicular to the plane. That's what we end up calling this line. A line that is normal, or that is perpendicular or orthogonal, if you want to use that word, to the tangent line is called the normal line. So we can pretty much write the equation of the normal line for free. We're going to use the same point, and because we know the derivative is the tangent line slope, all we have to do is figure out how to get a perpendicular slope from a given slope. How are perpendicular slopes related? They're at 90 degrees, but if I have the quantitative numerical value for one slope, how do you get the perpendicular slope from it? It is the opposite reciprocal. Yeah, it's the opposite reciprocal. So let's come back down here and throw in the normal line. We're still going to use the same point, 27, 5. You can call that now the point of normalcy if you want. And then the slope, I'm going to put m subscript n for the normal slope instead of the tangent line slope. The derivative always gives you the tangent line slope. So once we have it, the normal slope is going to be what? If the tangent line slope is 1/10. Negative 10. Right? It's the opposite sign and you flip it. Because it started positive, now it's negative. Because it was 1/10, now it's 10. And so here's the equation of the normal line right here. In Taylor form, it's y equals 5 minus 10 times x minus 27. It pretty much comes for free. In fact, in the Taylor form, the only difference is going to be the slope right there. Now, they do end up having different y-intercepts. If you were to distribute the slope and combine like terms, you would have different values of b in the y equals mx plus b form. But in Taylor form, because it's not expanded, that's the only thing that's different. So you get the normal line for free anytime you have the tangent line. Okay? All right, let's move on to another version of the derivative, because there's going to be 3 versions that you're responsible for. This was the first one yesterday. This is the standard formal limit definition. This one gives you a function of x. It gives you a function of x that we can use and reuse over and over and over again by just dropping in any old value of x we want. The next version, we're going to modify this by simply taking this x here, this x there, and that x there, and we're going to replace it with a specific value of x, like x equals 1 or x equals -3. In general, we call that value c. So this is called the modified form. The derivative f prime of c is the limit as h goes to 0 of f of c plus h minus f of c over h. So once again, the only difference from the formal definition is instead of x, we replace those with an actual number, okay? C is some x value. Now this one does not give you a function of x. This is a disposable version. You use it one time and it's done. It gives you a numeric slope. It gives a numeric value as a slope. So if you wanted to find the slope at more than one value of x, you would have to set up the limit and evaluate it over and over and over again. Whereas f prime of x, you do the calculations one time, and then you can plug in for x after the fact, okay? So let's try this out. Let's try out this modified form. On example 5, it says, for f of x equals x over x plus 1, find f prime of 1 directly by using the modified definition. All right, well, let's go ahead and write it out specifically for this function. F prime of 1, then, is going to be the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. So, again, the only difference from the formal definition is wherever we have the x, we now have a 1. Now let's evaluate it. We have the limit coming straight down here. To evaluate it at 1 plus h, I'm going to plug the 1 plus h into both values of x in my function f of x. So we're going to end up with 1 plus h all over 1 plus h plus 1. And then minus f of 1, you just plug it in and you get 1 over 1 plus 1. And all that is over h. So there's the setup. If you didn't simplify as you were setting it up, now's a good time to simplify. You can combine like terms. 1 plus h over 2 plus h minus 1 over 2 all over h. At this point, if you try to evaluate it by direct substitution, guess what you're going to get? 0 over 0. And that's great. That's good news to you now because that means you set it up correctly. We're going to kind of cleverly circumvent it, though, algebraically, the way we learned how to do it in 1.4. Lick 'em over lick 'em. Excellent. This is LCM over LCM. So your miniature denominators are just 2 plus h and 2. I guess if you want to put that over 1, you can. So the least common multiple of 2 plus h and 2 is their product. 2 times 2 plus h. 2 times 2 plus h. 2 times 2 plus h. Don't call it 2 plus 2 plus h because it's multiple. So now the algebra should be pretty straightforward since we've already practiced it. If you distribute, you're going to be left with 2 times 1 plus h in the first term, minus the 2's divide out, and you're left with 2 plus h behind the negative. So again, here's where you got to be careful. That's a minus. The 2's divide out, you're left with the quantity. And then all over h times 2 plus h, which I'll call 2h times 2 plus h. So that got rid of the complex fraction. Every complex fraction, lick 'em over lick 'em problem then turns into a little sledgehammer problem if you did not distribute as you wrote it down. So now we'll distribute the 2 and we get 2 plus 2h minus 2 minus h all over 2h times 2 plus h. When you do that, great things should happen. Your 2's will cancel and you're left with 2h minus h, which is what? H. So I'm going to bring it around over here. The limit as h goes to 0. We're just left with h over 2h times 2 plus h. And now the good news is the h's divide out, leaving a 1 in the top. And of course, once you get rid of the 0 over 0 problem, you can use direct substitution now on any h that's left. There is 1 right there, so we're left with 1 over 2 times 2, which is 4. Now here's a common mistake. I see it happen a lot of time when students are in a hurry. The h's divide out, so there's nothing left in the numerator, and they plug in a 0 for any h that's left, and they end up with an answer of 4, right? Because 2 times 2 is 4. Be very, very careful. If something divides out in the numerator, put a 1 there so that you realize it's still a fraction. It's still 1 over 4, not just 4. But there you go. That would be the slope of whatever this graph looks like at x equals 1. What can I tell you about the function at x equals 1? Well, I know that since this is a positive slope, the graph is whating, increasing or decreasing? It's increasing, right? Positive slope means the function's increasing there. Not too fast, right? It's going up 1 for every 4 it's going to the right, so it's kind of flat. Yes. Yes, you do. Again, this one is almost like the one we memorized yesterday. It's just plugging in a specific value of C. You do have to memorize it. This here? Well, here's my function, right? So remember that your function uses an x as a placeholder. But if you want, you could just call it f of blob equals blob over blob plus 1, right? We did that in pre-cal. And whatever you put in here, whether it's a number or a little blue star, you're going to plug it into the other places as well. So what are we plugging in into the first one? We're plugging in a 1 plus h, right? So f of 1 plus h is 1 plus h over 1 plus h plus 1. And that's what I got right there. And then minus, in the second one, we're just plugging in a 1. So that would be 1, 1, 1. And you get that right there. Why do we plug in a 1? Because it's asking us to find f prime of 1. Yeah, that's your C value. If it said find f prime of 2, we'd be plugging in a 2 for C. Yeah. So that's going to be given. So the slope of the graph at that point is 1/4. Now part B, it's going to ask you to find the equation of the normal line. It didn't even want the tangent line. It just wants the normal line. So again, what do we need for the equation of a line? Just in general? Slope and a point, right? You need slope and a point. The slope of the normal line is going to be related to the tangent line slope how? It's perpendicular, so instead of calling it m, I'm going to call it m sub n for the normal slope. If the slope of the tangent line at 1 was 1/4, what would be the normal slope then at the same place? -4. Good. The opposite reciprocal. And now the point is going to be 1 comma f of 1, which we have already found. F of 1, remember, is this point right here. It's 1/2. Or you could just plug it back into the original. 1 over 1 plus 1 is 1 over 2. All right, so now we're ready to go. The equation of the normal line is y equals the y value of 1/2 plus the slope, which is now -4, times x minus the x value of 1. There's the normal line. So on a test, on your next test, as a multiple choice question, I might just say, what is the y-intercept of the normal line to this graph at this point? You would have to then find the slope of the tangent line on your own, take the opposite reciprocal of it, find the y value by plugging the 1 into what was given, write the equation of the normal line to get that, and then once you have the equation, how do you find the y-intercept of any equation? Plug in a 0 for x. Good. If I ask you for the x-intercept of the normal line, you would set y equal to 0 and solve. So that's going back to Algebra 1. But it's just one more task that I can ask you. So these questions do have possibly multiple steps that you would have to map out on your own. But if you always begin with the end in mind, what do I need? I need the equation of a normal line. So I need a slope and a point. I can get the point by plugging in the 1, but I need the slope of the normal line. I'm going to get the slope of the tangent line first. That's the derivative. So now I need the derivative. I'll set it up and evaluate it. Okay. If I wanted to find the slope now at 2, I would have to set this whole thing up again for 2, lick 'em over lick 'em it, and come up with a different numeric answer. Whereas if I would have done f prime of x, instead of using 1s, use x's, I would now have a function into which I can just plug. But that's not what the question asks us to do. Well, when you're using the number 1 instead of the letter x, the calculations just get a little bit easier because you only have one unknown instead of 2. If you use x, you're going to have 2 variables, and so the calculations are not going to be difficult. You're a pro at them already, but they are easier if you can use a number instead of a variable. So if you were truly just interested in finding the slope of one graph at one point, you could use this, okay? But if you ever had the intention of doing more than one point, you're probably going to want to do the version up here because that's the only difference. All right, that one uses an x, this one uses a specific number. All right, so now here's the summary. Everything in this chart on the left column, you don't need calculus for. It's good old algebra. 2 points. The following are equivalent. The slope of the secant line, f of b minus f of a over b minus a, that's what we call the difference quotient, remember? The difference quotient. And the average rate of change on the interval. They're all equivalent. You don't need calculus for those. 2 points. Secant line, average rate of change. Delta y over delta x. That's essentially what the difference quotient is. Delta y over delta x. It's your algebra 1 slope. But now, the column on the right, with calculus, we could talk about instantaneous stuff. Things that happen at a single point or a single moment in time. The following are equivalent. The slope of the tangent line. That's Leibnizian perspective. The bottom says instantaneous rate of change. That's the Newtonian perspective. Here is the modified version. It gives you the numeric slope at that point. We call it f prime of c, also known as the derivative of the function at c. They're all really interchangeable. Mathematical synonyms, just different versions of the same thing. Okay, so truth be told, once we get going in Chapter 2, you're going to learn some easier rules to find derivatives, which are distillations of these definitions right here. So you're not going to have to necessarily find the derivative function or the numeric derivative slope by setting up and evaluating these limits. What you are responsible for is deconstructing them, recognizing those limits set up, and be like, oh, that limit is just the derivative of this particular function evaluated at that particular point. And once you have that recognized, then you're going to find the derivative using a shortcut rule instead of evaluating the limit. So that's what example 6 is asking you to do. Each of the following limits represents the derivative of some function, f of x, at some x value, call it c. In other words, they represent f prime of c for some function f of x at some c value. Your task is to identify the function whose derivative it represents and the value of c whose derivative value it's being evaluated at. The giveaway, if it hadn't said this, is h going to 0. College Board and I and most people use h exclusively to represent the limit definition of a derivative. Now this is the modified form. It has to be modified form because it represents the derivative of some function at some point. So take a look at it for a second and see if you can tell me what the function is whose derivative this is and what value of c it's being evaluated at. We're going backwards. We're deconstructing the limit. If you need a peek at modified form, it's right up here in the box. So that is basically the right side of this equation set up already, and we're trying to deconstruct it to find the c value and the f. All right, anyone think they have the c value? That's probably the easier of the two. 2. Good. And then what would be the function? Minus x plus 7. Fantastic. That's it. So moving forward, if I would have given you this function and said evaluate it using the modified form at x equals 2, you would set this up on your own and then evaluate it. Okay? So here's an easy way to do it. Really all you need to do is look at the first term. If you look at the first term in the modified form, this f of c plus h, that's enough to get you both the function and the c value. So all you have to do is come to your place where you have either x plus h or number plus h and cross it out and say, I don't like you, number plus h. And what do you do in the yearbook when you see someone you don't like? You X them out, right? Or you draw a mustache on them or something. Okay? In this case, we're going to say, I don't like you 2 plus h, and we're going to cross it out. And if you do that, what are you literally staring at now in the first term? 5x squared minus x plus 7. You're staring at the equation. And then to find the c value, hopefully you didn't obliterate that person's picture in the yearbook, right? Just draw an X through it so you can still see, oh, I obliterated that person, right? You can still see underneath the X here, if it's not x plus h, if it's a number plus h, that number, in this case 2, is the c value, all right? So this does represent f prime of 2 for the parabola 5x squared minus x plus 7. That's what you have to be able to do 3 weeks from now, 10 weeks from now, on May 15th, the morning of the AP exam. That, okay? Yes, at x equals 2, this would give you the instantaneous rate of change, the slope of the graph at that point, on that parabola graph right there. All right, so now that you kind of know how to do it, go ahead and do B and C and D on your own, and I'm going to give you, let's see, 30 seconds per for a minute and a half. And if you're watching the video at home, you don't even have to hit pause. You just try it on your own. Identify the function and the value of x where it's being evaluated. I don't like you, President. It's National Boyfriend Day, by the way, in addition to Caramel Custard Day. Well done. Good function. Good value. Ooh, I like 3 of the 4. B is the one that I'm a little bit kind of about. All right, the first one. You got the limit as h goes to 0. I don't like you pi fourths plus h. So you're staring at now f of x equals tangent of x, or is it tangent of x minus 1? Or is it just tangent of x? Or is it minus 1? Well, let's see. If this is correct and the function is tangent of x minus 1, remember that last number in the numerator should be f of c. I think it's pretty easy to see that the c value in this case is pi fourths. So could it be that it's tangent of x only and that 1 is f of pi fourths? Well, that would be tangent of pi fourths. What's tangent of pi fourths? 1. So that is exactly what that is. So we just want the first term, tangent of x minus tangent of pi fourths. So the function is not tangent of x minus 1, it's just tangent of x. Okay? Just tangent of x, and the c value is pi fourths. So this entire limit right here represents f prime of pi fourths for the function tangent of x. It gives you the slope of the tangent line at pi fourths. This one over here, a little bit easier. I don't like you pi plus h. You're staring at f of x equals e to the x. And the c value, if you peek underneath that x, is pi. So this must be f of pi, which would be e to the pi power, right? E to the pi plus h minus e to the pi. Very good. So if you got that, that's correct. F of pi plus h minus f of pi. Now the last one is a little bit tricky because it's the only one up here that doesn't have 2 terms in the numerator. I don't like you 1 plus h, so it could be that f of x is equal to the natural log of x, and c is equal to, peek under there, a 1. But how come there's no second term? It should be minus f of c, right? Minus f of c. Well, if the function is natural log and c is 1, how come there's no minus natural log of 1 there? It's 0. Yeah, very good. The natural log of 1 is 0. The h is not approaching x. The h is still approaching 0. I'm sorry, why is what?
Why is the h approaching 0 on the...
Oh, because it goes back to the same definition that we did yesterday, right? Where that second point, we're trying to find f prime of 1, let's say. We choose that other point to be 1 plus h. If we define that second point to be 8 units away, then we have a secant line now between the 2 points. But what happens when we let h go to 0? H is the distance between the 2 points. We let this point here that we have to use move closer and closer and closer to the point that we're interested in. And as h becomes 0, the point that we have to use, that we don't want to use, approaches the point that we're actually interested in, and the key there is that the secant slopes approach the tangent slopes. So h is just the distance between the 2 points. So letting one point approach another point is the same as letting the distance between them approach 0. So that comes from the definition. All right, very cool. That is very important. So how much time do we got left? We got a little bit of time left. As you're practicing in your worksheet tonight, I would find all the questions that involve this and see if you can get those answered while it's still fresh in your head. Okay, we're going to start talking about differentiability at a point, which I think we've already mentioned, right? A function is differentiable at a point if its derivative exists there. And we already saw up here the square root of x function. It was continuous at 2, but it was not differentiable at 2 because we had a vertical tangent line. So what we're going to do now is come up with an intuitive idea for differentiability, okay? Now remember that we also said that it was kind of pointless to even talk about the derivative existing way out here where there were no values to even talk about, right? So it turns out that if you want a function to be differentiable, it has to first be continuous. In other words, continuity at a point is a necessary precondition for something to be differentiable. But it's not sufficient, as we just saw. Just because it's continuous doesn't mean it's differentiable. But if it's not continuous, it's not going to be differentiable. It has to be continuous first. All right, so here's the intuitive definition of differentiability at a point. If we have a function that is continuous at a point, first and foremost, then to see if it's differentiable, all we have to do is take the limit from the left and right of the derivative function. That is, we're analyzing the slope from the left and comparing it to the slope from the right. And if it's continuous, number one, and the slopes are approaching each other from either side, then we're going to say that the function is differentiable there. So let's take a look at something. Let's say I have a parabola that turns into a line. Okay? Can anyone come up here and pinpoint exactly where it changed from being a parabola to a line? Can you pinpoint it exactly? It's probably somewhere in here, right? Maybe, or maybe somewhere in there. Yeah. You can't do it, okay, because we would say that this would be differentiable at x equals c. Not only is it connected, not only is it continuous, but the slopes from either side are merging in towards each other. They are making an allowance to try and smoothly connect. That's how you can spot it. If it's smoothly connected, the slopes are making an effort to try and merge into one another. But what if I drew a parabola and then turned it into a line? Can anyone now come up here and pinpoint exactly where it went from being a parabola to a line? Yeah, this was real obvious, right? Because even though it's connected right there, the slopes are not making any attempt to merge towards each other. In fact, the slope from the left of that point is some big positive number, and the slope on the right is some negative number, and no way a positive number is going to equal a negative number. So if you want to know if a function is differentiable at a point, you got to check. Is it connected? Is it continuous? And then, is it smoothly connected? Because if it's smoothly connected, now the slopes are going to be merging towards each other. So would you say the function is differentiable or not right there at x equals c? It is not differentiable. Good. So we now have two of them. A vertical tangent and now some kind of, we'll call that a sharp turn. If you have a sharp turn on a graph or some type of barb, something that you might imagine cutting yourself on if you touched it, right? The slopes are not going to be merging towards each other. All right, so let's go ahead and check out example 7 based upon this intuitive idea. Let f be a continuous function. If it says it's a continuous function, it means it's continuous where? Everywhere. It means for all x. If it doesn't specify, you can assume it means for all x. We want to then determine if each of these functions whose derivative is given are differentiable or not at x equals 1. So we know they're already continuous. Okay, that's good. They have to be continuous. we're given the derivatives f prime. So based upon this, all we have to do is check now to see if the slopes from either side are becoming the same thing. And we're going to do that by finding the one-sided limits of f prime. So here we go. On part A, the limit as x approaches -1 from the left of f prime, much like we would do for continuity. Direct substitute in, and you get +1. So this function's connected, and as the graph comes in from the left side of -1, the slopes are gradually merging into a slope of 1. Let's see what happens on the other side. The limit as x goes to -1 from the right-hand side of f prime of x. You plug in your -1 on this side, and you get -1 squared, which is 1. Does 1 equal 1? Yeah. So here's what we're going to say. Since 1 equals 1, and since f is continuous, comma, f is differentiable, and I'm going to abbreviate differentiable, diffable, with a little hyphen to show some letters have been omitted. Feel free to do that too, except on International Day of Non-Abbreviation, which is May 15th, the day of the AP exam. Since 1 equals 1, and since f is continuous, f is differentiable now at x equals -1. So it's kind of like the three-step definition of continuity, but it's really just a two-step definition for differentiability. We're already assuming it's continuous. All we have to do is check the slope from the left, the slope from the right. And because they're the same, now we can actually claim that the slope equals something at a particular value of x. All right, let's try this one. Last one for the day and we'll be done. We know f is already continuous. We just got to check the slopes at -1. So the limit as x goes to -1 from the left of f prime of x, and the limit as x goes to -1 from the right-hand side of f prime of x. Go ahead and calculate those on your own. I'll give you 1 minute, and then we'll conclude the day's lesson. Negative pi, yeah, what is it? You go in clockwise? It's coterminal with positive pi, yeah. Yep, so that's the right first value. Yeah. Negative pi, you're just rotating clockwise pi units. It's coterminal with pi. So now you just got to figure out what the cosine of pi is. It's the same as cosine of negative pi. Cosine's an even function, remember? All right, most of y'all got the first one pretty well. It's the natural log of 2 minus 1, which is 1. The natural log of 1 is a numeric answer, but it's not best for comparing things, is it? So the natural log of 1 is 0. Y'all should know that. Most of y'all did. Plug in a -1 here, and you get cosine of negative pi. That on the unit circle is over here, and the ordered pair is -1, 0. Cosine, of course, then is -1. Does 0 equal -1? No. So the slopes are not making an effort to merge into each other. It's still connected, but the slopes aren't the same. So that's going to look kind of like this did up here. So now we're going to say, since 0 does not equal -1, comma, f is not differentiable or diffable. F is not diffable at x equals -1. It's continuous still, but not differentiable. It's connected, but not connected how? Smoothly. Right. Okay. We'll stop right there, and we'll pick up tomorrow with the third and final limit definition of the derivative that you're responsible for knowing. It would be a stretch if we did. I'm not counting on it. I would say that for sure we'll finish the notes on Thursday. Looks like the worksheet will be due on Friday. And we'll quiz on Friday as well.